This is part 2 of my video on the 3 levels of the Kelly Criterion. We discuss how the Kelly Criterion relates to the Sharpe Ratio and the fractional Kelly Criterion strategy. If you've watched the first video, feel free to skip to the next section. If you haven't watched it yet, here's a recap. In level 1, we explained the basic Kelly Criterion formula to help us make the smartest bet in a casino. Suppose there's a game with a winning probability P and a losing probability Q, which equals 1 minus P. If we win, we gain a fraction G of our bet. If we lose a fraction L of our bet. What fraction F of our wealth do we bet to maximize our return? Our geometric average return in one round is 1 plus Fg to the power P times 1 minus Fl to the power Q. Taking the logarithm and then setting the derivative equal to 0, we get the optimal fraction P over L minus Q over G. In level 2, we explain the Pro-Epstein's paradox and the concept of wealth. Most people focus on the fraction part of the problem statement but miss the wealth part. It turns out that wealth is not the same as the amount of cash you have. In level 3, we extended the Kelly Criterion from 2 outcomes to a continuous distribution of outcomes. Assuming the outcomes are in the range from A to B, and the outcomes follow a probability distribution function P of t. The log return is the integral from A to B of P of t times log 1 plus ft dt. We take the derivative and then set it equal to 0 and then solve for f. In the previous video, we considered a stock with returns that follow a normal distribution with mean mu and standard deviation sigma. I teased that the optimal fraction f is the Sharpe ratio divided by the standard deviation. But how can we actually solve for f? There is one technique that leads to interesting results. Let x be a random variable with mean mu. It has a 50% probability of being mu plus sigma and a 50% probability of being mu minus sigma. The standard deviation of x also turns out to be sigma. We apply this approximation to the stock's return. In finance, there's a concept called the risk-free rate. The risk-free rate represents the return on an investment with zero risk. You can think of it as the interest on your bank's deposit or the yield on a US government bond. Suppose we invest a portion F of our wealth into the risky stock and deposit the remaining 1 minus F portion into a bank that pays the risk-free rate. Our gain from the risk-free rate is guaranteed to be 1 minus F times our F. We earn either F times mu plus sigma or F times mu minus sigma from the stock with equal probability. Therefore, our return R is one of the following 2 cases with equal probability. Let's draw a graph to see how our wealth grows with time. The green line shows our gain and the red line shows our loss. Obviously, this isn't how the stock market works. A stock moves up and down very frequently. Therefore, we subdivide the time interval into n equal independent steps. We start from n equals 1 and gradually we increase to n equals 10. The bigger the final dot, the higher the probability of getting to that state. As n grows larger, our wealth changes more quickly. You can imagine when n goes to infinity, our wealth changes continuously, just like in the stock market. As a technical note, stock prices actually follow a jump-diffusion process, but in our case, we ignore the jumps and only consider the continuous movements. Back to the formulas. Our geometric average return is calculated as follows, just like in the previous video. The exponents refer to the probabilities of the scenarios happening, which are 0.5 for both. If we subdivide the time interval into n steps, then for each step, the mean goes from mu to mu over n. The variance goes from sigma squared to sigma squared over n, and the risk-free rate goes from Rf to Rf over n. We have n total steps, so the cumulative return after all n steps is obtained by raising to the nth power. 0.5 becomes 0.5n in the exponents. Again, we take the logarithm on both sides. To make this approximation as accurate as possible, we take the limit as n goes to infinity. Then, each discrete step will be so small that it is no different than a continuous distribution. Before we continue, let's look at the following formula first. I promise it will be useful. This is the Taylor series expansion for log 1 plus x. If x is equal to this yellow expression, the first term of the series is the same expression, and the second term can be calculated as follows. We denote all the terms of order -3/2 or smaller as O of n to the power -3/2. This means that as n goes to infinity, these terms are so small that they can be ignored in our calculations. Similarly, if we let x to be this blue expression, we have the following series. Returning to our formula for log r, we can substitute the Taylor series expansions into the formula and simplify. As n goes to infinity, O of n to the power -1/2 approaches 0. We get this quadratic equation in terms of f. Let's look at the graph. We see that the maximum of log r is at the top of this curve, where the derivative is 0. Therefore, we take the derivative and set it equal to 0. Mu minus rf minus sigma squared f equals 0. Solving for f, we get f equals mu minus rf over sigma squared, or the Sharpe ratio over the standard deviation. This answers our question from the last video. Next, let's talk about the fractional Kelly criterion. In the real stock market, we never know the true mu. What if we overestimate it? The fractional Kelly criterion helps us solve this problem. In the stock market, people tend to be over-optimistic. We often overestimate potential returns and underestimate the risks. Therefore, to be safe, sometimes we only bet half of the Kelly fraction or even just a quarter of the Kelly fraction. Look at this graph and you'll see how it makes sense. This curve shows the log return when mu equals 0.1 and standard deviation equals 0.5. We take the risk-free rate to be 0. The Kelly fraction is at the top of this curve. When we bet the Kelly fraction, represented by this green line, we're assuming our prediction of mu is accurate. But if the actual mu is only half of what we predicted, the correct curve shifts to this yellow one. In this case, we lose out on some of the potential returns. In a more extreme scenario, where the actual mu is only a quarter of our prediction, our returns turn negative. Now let's consider betting half of the Kelly fraction. If our prediction of mu is accurate, we won't be maximizing returns. However, if the actual mu is only half of our prediction, the green line aligns perfectly with the peak of the yellow curve, meaning we are exactly at the optimal fraction. And if the actual mu is just a quarter of our prediction, our returns are no longer optimal, but at least we avoid negative returns. Finally, let's take a more conservative approach and bet only a quarter of the Kelly fraction. If the actual mu is half of our prediction, we'll still miss out on some returns. But if the actual mu drops to a quarter of our prediction, this fraction turns out to be optimal. Notice that the more we bet, the worse our returns get when we are wrong. In summary, if we bet only a fraction of the optimal Kelly fraction, we get worse returns when we are right, in exchange for better returns when we are wrong. You're watching Luck by Numbers. If you enjoyed this video, please like, subscribe, and share your thoughts below. Also, check out the first part if you haven't already.